A leaf twitches, but not from wind. The movement is too precise, too economical. An arc that exists for less than the blink it takes to notice it. Flesh meets air meets fangs, and the event is already over before the mind assigns it a name. What remains is not the strike, but the delay, an empty fraction of time in which a human brain is still deciding whether there was ever a threat at all. In that silent gap between sensation and understanding, a system perfected over millions of years completes its task with mechanical certainty. This is not speed as we understand it. It is the erasure of reaction itself, a biological solution that does not outpace its target so much as it bypasses the need for pursuit altogether. The human nervous system is built for interpretation, not immediacy. Sensory input must travel through layers of processing, retina to cortex, signal to perception, before a decision can even begin to form. Even at peak readiness, the fastest voluntary response lingers in the realm of tenths of a second, a delay measured in the slow language of muscles, waiting for instructions. But in the coiled stillness of a viper or the poised tension of a mamba, there is no such hesitation. The strike is not a reaction, it is a release. Energy is stored in advance, preloaded into a lattice of muscle fibers, arranged along an S-shaped curve that functions less like a limb and more like a compressed spring. When triggered, that stored energy converts instantly into motion, bypassing the metabolic lag that governs most vertebrate movement. The result is a burst so brief that high-speed cameras, not human perception, are required to fully witness it. In the heavy, leaf-littered forests of Central Africa, the Gaboon viper lies in wait, its body disguised as decay itself. Its geometry is deceptive, broad, triangular head merging seamlessly into a body patterned with fractal precision, a visual disruption that dissolves its outline into the chaos of the forest floor. But camouflage is only the first layer of its strategy. The true weapon is temporal. When the strike begins, it unfolds with a velocity that collapses distance into irrelevance. The fangs, among the longest of any snake, do not precede the motion. They deploy during it, rotating forward as the jaws open in a synchronized mechanism that transforms the head into a delivery system. Venom is not dripped or absorbed. It is injected, forced through hollow channels under pressure, a biological analog to a hypodermic needle designed for immediate transfer. In this moment, the distinction between predator and instrument disappears. The snake is not chasing prey, it is executing a preloaded command. Across the savannas and scrublands, the western diamondback rattlesnake operates under the same principle, but with a different interface. Here, the environment is more open, the visual field less cluttered, and the warning system, its iconic rattle, introduces a paradox. The sound suggests hesitation, a chance for avoidance, a signal that seems almost generous in its transparency. But this is not mercy, it is efficiency. The rattle reduces unnecessary conflict, conserving venom and minimizing the risk of injury. Yet when that warning is ignored, or when surprise overrides protocol, the strike that follows is identical in its temporal ruthlessness. Coiled beneath a geometry of tension, the body releases itself with explosive precision. The arc is short, the contact fleeting, and the withdrawal immediate. In less time than it takes for a human to flinch, the transaction is complete. The physiology that enables this is not merely muscular, but neurological. These reptiles operate on a system of pre-programmed responses, where the threshold for action is calibrated through evolutionary pressure, rather than conscious deliberation. Sensory input does not climb a hierarchy of interpretation. it triggers a cascade. In pit vipers, specialized organs located between the eye and nostril detect infrared radiation, allowing the snake to perceive the thermal signature of living organisms even in complete darkness. This is not vision in the traditional sense, but a parallel sensory channel, one that translates heat into spatial awareness. A warm-blooded animal moving through the environment becomes a luminous target against a cooler background, its position mapped with remarkable accuracy. The strike, when it comes, is guided not by sight alone, but by a fusion of sensory inputs that reduce uncertainty to near zero. In the realm of the black mamba, the equation shifts again, not in speed, but in persistence. Unlike the ambush specialists that rely on a single decisive moment, this species embodies a different philosophy of lethality. Its body is elongated, its movement fluid and continuous, allowing it to traverse ground with a velocity that transforms the landscape into a network of reachable points. When threatened or engaged, it does not rely on a single strike, but on repetition, a rapid succession of bites delivered with escalating intensity. The venom, primarily neurotoxic, targets the nervous system directly, interfering with the transmission of signals between neurons and muscles. Paralysis is not a side effect, it is the objective. In this context, speed is not only about the strike, but about the accumulation of effect, a compounding assault that overwhelms biological systems faster than they can compensate. Yet beneath these variations in behavior lies a shared architecture of intent. The strike is often framed as the climax of predation, the moment of violence that defines the encounter. But this perspective misunderstands the system. The strike is not the primary challenge these animals have solved. It is the final expression of a deeper problem: how to convert stored energy into effective action with minimal delay. Every aspect of their biology, from muscle fiber composition to neural circuitry, serves this objective. Even the shape of the skull, with its kinetic joints and flexible ligaments, is adapted to maximize the efficiency of this singular event. The snake does not think its way into a strike. It exists in a state of readiness, a poised equilibrium where the boundary between stillness and action is almost non-existent. This creates a dynamic in which the true danger is not the visible behavior, but the invisible preparation. To an observer, the snake appears motionless, a static element within the environment. There is no obvious buildup, no gradual escalation that signals impending action, but this stillness is deceptive. It is not inactivity, it is stored potential. The muscles are already engaged, the nervous system already primed, the sensory apparatus already scanning for the precise conditions that will trigger release. When those conditions are met, the transition from rest to motion is instantaneous because the system has been prepared in advance. The strike does not begin when it is seen. It begins long before, in the silent accumulation of readiness that precedes it. This is where the human perspective fails most dramatically. Our perception is tuned to changes we can detect, movements we can track, sequences we can interpret. We expect cause to precede effect in a way that allows for anticipation, but in the world of these reptiles, cause and effect collapse into a single moment. By the time the brain registers the presence of a threat, the outcome has already been determined. The delay is not just a limitation, it is a vulnerability, one that these animals exploit with ruthless consistency. In evolutionary terms, the advantage is absolute. A predator that can bypass the reaction time of its prey does not need to be stronger, faster over distance, or more enduring. It only needs to be precise. And yet, this precision introduces a reversal that reshapes the narrative entirely. The strike, for all its speed and lethality, is not the most dangerous component of the system. It is the most visible, the most dramatic, and therefore the most misleading. The true hazard lies in the invisibility of the preparation, in the fact that the event is decided before it is perceived. What kills is not the motion itself, but the absence of warning, the gap between reality and recognition. In that gap, these animals have carved out a niche where survival is determined not by who reacts faster, but by who never has the chance to react at all. The branch bends under a weight that should not be there, a subtle shift against the stillness of coastal wind, and somewhere above the forest floor, a bird makes the smallest mistake of its life. It lands for less than a second, wings folding, claws tightening on bark that has already been claimed. What follows is not a chase, not even a visible attack, but a rupture in time, a flicker of motion so compressed that the eye registers only the aftermath. Feathers scatter, the body convulses, and the predator has already withdrawn, coiled once more into the geometry of patience. In that instant, venom begins its work, not as a slow poison, but as an engineered collapse of biological function. This is not predation as a sequence. It is predation as an inevitability, a system refined to remove uncertainty from the act of killing. On a remote outcrop in the Atlantic, cut off from the Brazilian mainland since the end of the last glacial period, the golden lancehead exists as the product of a closed equation. Rising sea levels isolated this fragment of forest, severing it from the ecological networks that once balanced its inhabitants. Mammalian prey disappeared, unable to sustain viable populations in such confined space. And with their absence, the food web collapsed into a simpler, more volatile configuration. What remained was a vertical world dominated by branches, leaves, and the transient passage of migratory birds. In this new system, survival no longer depended on overpowering terrestrial prey, but on intercepting fleeting opportunities in the canopy. The island did not just isolate a species, it redefined the parameters of existence, forcing evolution to operate within the constraints of scarcity and unpredictability. The result is not merely a snake that is more dangerous, but a snake that is more specialized, its entire physiology recalibrated for a single ecological niche. Birds, unlike ground-dwelling mammals, do not linger. They arrive exhausted from long-distance flight, rest briefly, and depart. A predator that fails to incapacitate such prey immediately loses it to the sky, along with the energy invested in the attempt. Under this pressure, venom evolves not as a general-purpose toxin, but as a rapid-acting biochemical weapon optimized to disrupt critical systems before escape becomes possible. The hemotoxic compounds, delivered by the golden lancehead, do more than damage tissue. They interfere with the very mechanisms that maintain circulatory stability, breaking down blood vessel integrity and triggering cascades of coagulation and hemorrhage. In evolutionary terms, speed of effect becomes as important as potency, transforming venom from a deterrent into a precision tool designed for instantaneous outcomes. This biochemical refinement is mirrored by a shift in behavior that distinguishes the island population from its mainland relatives, such as the Bothrops jararaca, where the latter remains largely terrestrial, operating within the leaf litter and undergrowth. The golden lancehead has moved upward, occupying the arboreal layer, where its avian prey is most vulnerable. This transition is not trivial. Life in the trees demands different strategies of balance, camouflage, and strike mechanics. The body must anchor itself along narrow supports, distributing weight in a way that maintains both stability and readiness. The strike itself becomes a three-dimensional calculation, executed from above or at an angle rather than from the horizontal plane. Each successful adaptation reinforces the next, creating a feedback loop in which specialization begets further specialization, narrowing the ecological role while enhancing efficiency within it. The density of predators on this island amplifies these dynamics to a level rarely observed in natural systems. With limited space and a finite resource base, the population of golden lanceheads exists at a concentration that defies the typical constraints of predator-prey ratios. While early accounts exaggerated the numbers to almost mythic proportions, the underlying reality remains extraordinary. A landscape where encounters with these snakes are not rare events, but expected conditions. This density introduces a new layer of competition, not for territory in the traditional sense, but for access to the brief windows of opportunity presented by passing birds. In such an environment, hesitation is not merely a disadvantage, it is a failure to survive. Every individual is shaped by the same relentless pressure to act quickly, to strike decisively, and to secure energy in a system that offers no guarantees. Human interaction with this environment is, by necessity, restricted to the margins. The Brazilian government has designated Ilha da Queimada Grande as a protected area, limiting access to authorized researchers whose work is conducted under strict protocols. This restriction is often framed in terms of danger, and the danger is real. But it also reflects a deeper recognition of the island's scientific value. Here, evolution is not an abstract concept, but a visible process, its outcomes etched into the morphology and behavior of a single species. To disturb this system is to risk altering a living experiment that has unfolded over thousands of years, a rare opportunity to observe how isolation and constraint can drive biological innovation to its extremes. The venom of the golden lancehead, when introduced into a human body, reveals the same efficiency that defines its ecological role. Hemotoxic components begin to degrade tissue at the cellular level, disrupting membranes and initiating localized necrosis that can spread if untreated. Simultaneously, the circulatory system is thrown into disarray, with clotting factors activated and consumed in a chaotic sequence that can lead to both excessive bleeding and dangerous blockages. The body's attempt to maintain homeostasis becomes part of the problem, as regulatory mechanisms are overwhelmed by the precision and potency of the toxin. In clinical terms, the outcome depends on dose, location of the bite, and the speed of medical intervention. In ecological terms, such effects are not designed for humans at all. They are the byproduct of a system optimized for a different target, one whose physiology demands rapid incapacitation rather than prolonged suffering. What makes this island truly hostile is not simply the presence of venomous snakes, but the absence of counterbalance. In most ecosystems, predators are embedded within networks that include competitors, prey, and environmental factors that regulate their numbers and behavior. Here, those networks have been simplified to the point where a single species dominates, its influence extending across the entire landscape. The forest is not a neutral backdrop, but a medium through which this dominance is expressed. Each branch a potential ambush site, each patch of sunlight a temporary refuge for passing birds that may never leave. The usual checks and balances that prevent any one species from overwhelming an environment are reduced, allowing the golden lancehead to occupy a position that is both apex and anomaly. And yet, within this apparent excess lies a subtle reversal that reframes the entire system. The very specialization that makes these snakes so effective also renders them vulnerable in ways that are not immediately obvious. Their reliance on migratory birds ties their survival to patterns that extend far beyond the island itself, linking their fate to climatic shifts, habitat changes, and disruptions along migratory routes that they cannot influence. A decline in bird populations, whether due to environmental change or human activity, would ripple through this isolated ecosystem with disproportionate force. The predator, seemingly dominant within its confined domain, is in fact dependent on a network that exists largely outside its control. What appears as excess is, at a deeper level, a finely balanced equation, one in which even small perturbations can have cascading effects. This tension between dominance and dependence defines the island in ways that challenge conventional narratives of predation. The golden lancehead is not simply a more dangerous version of its mainland relatives. It is a species pushed to the edge of its adaptive capacity, its success contingent on a narrow set of conditions that must remain stable for the system to persist. Evolution, in this context, is not a steady progression toward greater complexity or power, but a series of compromises shaped by constraint. Each adaptation solves one problem while introducing new dependencies, creating a web of relationships that is both efficient and fragile. In this light, Ilha da Queimada Grande becomes more than a location. It becomes a demonstration of what happens when evolutionary processes are confined, accelerated, and stripped of redundancy. The result is a landscape where life operates at the limits of its design, where predators achieve extraordinary efficiency at the cost of flexibility, and where the absence of balance creates a form of order that is both compelling and precarious. The island does not offer a lesson in danger alone, but in the dynamics of specialization, the trade-offs that define survival, and the ways in which isolation can transform a species into something that exists nowhere else on Earth. On this island, evolution did not settle for equilibrium. It pursued a narrower path, one that leads not to stability, but to intensity. In doing so, it produced a system that feels excessive to the human observer, a concentration of predatory capability that seems almost disproportionate to the scale of the environment. Yet this excess is not accidental. It is the logical outcome of constraints applied over time, a reminder that when options are limited, life does not retreat. It adapts, refines, and in rare cases, such as this, becomes something that appears almost too efficient for its own good. The forest does not erupt with motion. It tightens. A ripple travels through leaf litter, subtle and deliberate, as something unseen commits to a direction till before the surface world registers the disturbance. Ahead, another snake pauses, its body tasting the air with rhythmic precision, unaware that it has already been selected. There is no ambush in the traditional sense, no explosive strike that ends the encounter in an instant. Instead, there is pursuit, slow, measured, and impossibly patient. The hunter is not reacting. It is calculating, adjusting its path through a sensory landscape that exists beyond sight. In this moment, predation is no longer about speed. It is about decision-making, a sequence of choices unfolding in silence, each one informed by a nervous system capable of more than instinct alone. Within the humid forests and agricultural edges of Southeast Asia, the king cobra occupies a role that challenges the conventional limits of reptilian behavior. Its size alone disrupts expectation, a body that can extend to lengths unmatched by any other venomous snake, allowing it to elevate a significant portion of itself above the ground. When it rises, it does not simply display. It redefines the spatial relationship between predator and potential threat, bringing its sensory organs into alignment with the vertical world of mammals. This capacity is not merely intimidation, it is information gathering, a way of sampling air currents and visual cues at a height where signals are clearer and more consistent. The hood, often interpreted as a defensive flourish, functions as both a visual amplifier and a structural support, stabilizing the anterior body during prolonged elevation. But it is not the physical presence of the king cobra that sets it apart. It is the way it interacts with its environment, a pattern of behavior that suggests a level of processing beyond reflex. Unlike ambush predators that rely on chance encounters, this species engages in active searching, moving through its territory with a purpose that appears directed rather than random. Chemical cues left by other snakes, microscopic traces deposited along the substrate, are detected by the forked tongue and analyzed through the vomeronasal system, allowing the predator to construct a map of recent activity. This is not tracking in the mammalian sense, driven by sight or sound, but a form of chemosensory interpretation that reconstructs the movement of prey over time. The king cobra does not simply encounter its target, it finds it. This distinction becomes critical when considering its diet. The term ophiophagy, the consumption of other snakes, describes more than a preference. It defines an ecological niche in which the predator is both competitor and regulator, feeding on species that share its environment and, in some cases, its capacity for venom. Encounters with the monocled cobra illustrate this dynamic with particular clarity. Here, two venomous systems intersect, each capable of delivering a potentially lethal dose, yet one is consistently subordinated to the other. The king cobra's resistance to certain venom components is not absolute immunity, but a partial tolerance, enough to reduce the risk of fatal envenomation during the struggle. Combined with its size advantage and precision in targeting the head region of its prey, this tolerance shifts the balance decisively. What appears as a hazardous confrontation becomes, through evolutionary refinement, a controlled interaction. The mechanics of such predation differ fundamentally from the rapid strikes observed in other venomous snakes. The king cobra often employs a strategy of repeated biting, maintaining contact with its prey and delivering successive doses of venom until neuromuscular function begins to fail. The neurotoxins involved interfere with synaptic transmission, blocking the signals that allow muscles to contract. Paralysis emerges not as a sudden collapse, but as a progressive loss of control, a shutting down of the communication pathways that sustain movement and respiration. In this context, the quantity of venom delivered becomes more significant than its per-unit potency. The snake compensates for lower relative toxicity by ensuring that enough of the compound enters the system to achieve the desired effect. Yet the narrative of the king cobra is not confined to predation. It extends into a domain rarely associated with reptiles: parental investment. Among snakes, reproductive strategy typically favors quantity over care, with eggs deposited and abandoned to environmental conditions. The king cobra diverges from this pattern in a way that suggests a different allocation of energy and risk. The female constructs a nest, gathering leaf litter and organic debris into a mound that functions as both protection and incubator. As the material decomposes, microbial activity generates heat, creating a stable thermal environment that supports embryonic development. This behavior integrates the snake into a broader ecological process, harnessing the metabolic activity of decomposers to regulate temperature in a manner analogous to the brooding of birds. During this period, the female remains in close proximity to the nest, exhibiting a level of vigilance that contrasts sharply with the typical reptilian model. Potential threats are met not with avoidance, but with confrontation, the body raised and the hood expanded as a signal of readiness. This defensive posture is not indiscriminate aggression, but a targeted response to protect a significant investment of energy. The eggs represent not just potential offspring, but the continuation of a lineage that depends on successful incubation in a variable environment. And yet, as hatching approaches, the female departs, relinquishing control at the threshold of a new phase. This withdrawal is not abandonment in the human sense, but a transition dictated by instinct, preventing the possibility of accidental predation on the emerging young. The presence of prey, such as the rat snake, further illustrates the flexibility within the king cobra's feeding behavior. While specialized in consuming other snakes, it does not exclude alternative targets when available, adapting its strategy to the local abundance of potential food sources. This opportunism enhances its resilience in environments where prey populations fluctuate, allowing it to maintain energy balance despite changes in the composition of the ecosystem. In doing so, it participates in a network of interactions that extend beyond simple predator-prey relationships, influencing the distribution and behavior of multiple species within its range. Human encounters with the king cobra reveal another layer of complexity, one that often contradicts the narratives of indiscriminate danger associated with venomous snakes. In many cases, the animal exhibits avoidance, retreating from perceived threats when escape is possible. This behavior reflects a cost-benefit analysis embedded within its neural circuitry, where the risk of injury or energy expenditure is weighed against the need to defend territory or offspring. However, when cornered or provoked, the response shifts dramatically. The snake stands its ground, elevating its body and maintaining visual contact with the source of disturbance. This escalation is not a loss of control, but a calculated decision, a threshold crossed when the conditions favor confrontation over retreat. This capacity for conditional behavior introduces a reversal that reframes the entire concept of danger. The king cobra is not the fastest striker, nor does it possess the most potent venom in absolute terms. Its advantage lies in the integration of multiple traits, sensory acuity, behavioral flexibility, and physiological adaptation into a coherent system that can respond to a range of scenarios. Where other snakes rely on a single decisive moment, this species navigates a sequence of possibilities, adjusting its actions in real time based on the information available. The result is a form of predation that is less about overwhelming force and more about informed execution. Within this framework, intelligence is not an abstract quality, but a functional attribute expressed through the ability to process environmental cues and modify behavior accordingly. The king cobra does not plan in the way humans understand planning, but it exhibits patterns that suggest a level of decision-making beyond simple stimulus response mechanisms. It selects, pursues, and engages with a degree of specificity that reflects an internal representation of its surroundings, a model constructed from sensory input and past interactions. This representation allows it to operate effectively in complex environments where unpredictability is the norm. The implications of this become clear when considering the broader ecological context. As a predator that targets other snakes, the king cobra influences the composition of the reptile community, potentially regulating populations that might otherwise expand unchecked. This role introduces indirect effects that ripple through the ecosystem, altering competitive dynamics and shaping the distribution of species. In this sense, the king cobra is not merely a participant in the food web, but a modulator of its structure, an agent whose behavior has consequences that extend beyond immediate predation events. And yet, despite this influence, the species remains subject to the same constraints that govern all life: habitat loss, human encroachment, and environmental change impose pressures that can disrupt the delicate balance it maintains. The intelligence that allows it to navigate immediate challenges does not confer immunity to large-scale alterations in its environment. In this respect, the king cobra embodies a paradox, a creature of remarkable capability operating within a system that is increasingly shaped by forces beyond its control. The final understanding emerges not from its size, its venom, or even its unique behaviors, but from the way these elements converge into a single, adaptive strategy. The king cobra does not dominate through speed alone, nor through toxicity in isolation. It succeeds by integrating information, by responding to context, and by making decisions that align with the conditions it encounters. In a world where many predators rely on fixed patterns, this flexibility becomes a defining advantage. The most dangerous reptiles are not those that strike the fastest or carry the most potent venom. They are the ones that interpret their environment, that adjust their actions with precision, and that choose the moment of engagement with an awareness that transcends reflex. In the silent calculations of the king cobra, danger is not an accident, it is a decision. A foot presses into sand that looks empty, and the ground answers with a sound before it answers with a strike. It is not loud, just a dry rasp, a friction of scales against dust, but it is the only warning the nervous system will receive before the event is already in motion. The body beneath the surface is not retreating, it is coiling, converting stillness into stored force, aligning bone and muscle into a geometry that exists for a fraction of a second. The bite lands and withdraws with the same motion, leaving behind a pair of punctures so small they seem insignificant, almost dismissible, until the physiology beneath the skin begins to reorganize itself in response. What follows is not always immediate collapse. Sometimes it is something more deceptive, a window, brief and narrowing, in which nothing feels final, yet everything already is. Across the arid landscapes of Australia, the inland taipan exists as a paradox that undermines the most common human assumption about danger. Its venom is among the most potent delivered by any terrestrial snake, a complex mixture of neurotoxins and procoagulants that can disrupt muscular control and blood function with remarkable efficiency. On a purely biochemical level, it represents an extreme, a refinement of toxicity that pushes the limits of what venom can achieve. And yet, within its remote habitat of floodplains and sparsely populated regions, encounters with humans are rare. The snake does not seek out conflict. It avoids it, retreating into burrows and cracks when disturbance is detected. Its existence demonstrates a critical distinction. The capacity to inflict harm is not the same as the likelihood of doing so. In isolation, potency is an incomplete measure of risk. This distinction becomes clearer when viewed alongside the saw-scaled viper, a species that operates at the opposite end of the spectrum. Its venom, while dangerous, does not reach the same level of per-drop toxicity as that of the inland taipan. Its body is smaller, its range more fragmented, its presence less dramatic in appearance. And yet, in terms of human impact, it stands among the most consequential snakes on Earth. The reason lies not in what it can do, but in where it exists, distributed across regions of Africa, the Middle East, and the Indian subcontinent, it inhabits landscapes that overlap extensively with human activity, fields, villages, and pathways where daily life unfolds. Its behavior compounds this overlap. Unlike species that rely on concealment alone, the saw-scaled viper employs a defensive display, rubbing its serrated scales together to produce a distinctive rasping sound that signals its readiness to strike. This warning, however, is often too subtle or too late to prevent contact. In this context, the concept of the 10-second rule emerges not as a precise measurement, but as a cognitive frame, a way of understanding the critical interval between envenomation and irreversible physiological change. It is not that death or permanent damage occurs within a fixed number of seconds, but that the trajectory of the outcome is established almost immediately. Venom begins to diffuse through tissue, entering the bloodstream or lymphatic system, interacting with cellular targets in ways that are both rapid and complex. In the case of hemotoxic venoms, such as those delivered by many vipers, the effects include disruption of blood clotting mechanisms, leading to a paradoxical state in which the body both clots excessively and bleeds uncontrollably. Microclots can form within vessels, impairing circulation, while clotting factors are simultaneously depleted, increasing the risk of hemorrhage. The visible symptoms, swelling, discoloration, pain, are only the surface expression of a deeper systemic shift. The Indian cobra introduces a different physiological pathway, one that targets the nervous system directly. Its venom is primarily neurotoxic, interfering with the transmission of signals at the neuromuscular junction. By binding to receptors that normally respond to neurotransmitters, these toxins prevent the activation of muscle fibers, leading to progressive paralysis. The sequence often begins with subtle signs: drooping eyelids, difficulty speaking or swallowing, and can advance to respiratory failure as the muscles responsible for breathing lose their function. In environments where medical intervention is delayed, this progression can be fatal, not because the venom destroys tissue in the way hemotoxins do, but because it interrupts the most fundamental processes required for life. The comparison between these venom types reveals a broader principle. Danger is not a single dimension, but a convergence of factors, including toxicity, delivery, behavior, and critically, proximity to humans. A snake with highly potent venom but limited interaction with people poses a different level of risk than a less toxic species that shares space with dense human populations. This is why the saw-scaled viper, despite its smaller size and less potent venom, accounts for a significant proportion of snakebite incidents in certain regions. Its ecology intersects with human routines: walking, farming, gathering, creating frequent opportunities for accidental encounters. The bite, in these cases, is not an act of predation, but a defensive response, triggered by contact or perceived threat. Understanding why bites occur requires a shift in perspective from viewing snakes as aggressors to recognizing them as reactive components of their environment. Most venomous snakes do not seek out humans as prey. Their sensory systems are tuned to detect smaller animals that fit within their dietary range. When a human steps on or near a snake, the resulting bite is a last resort mechanism, an attempt to neutralize what the snake perceives as a large, potentially lethal threat. This defensive context explains patterns observed in snakebite incidents, which often involve lower limbs and occur during activities that bring people into direct contact with the ground. The snake's response is immediate because hesitation would increase its own risk of injury or death. The effectiveness of anti-venom introduces another layer to this system, one that bridges biology and human innovation. Antivenoms are produced by exposing host animals to controlled doses of venom, allowing their immune systems to generate antibodies that can later be harvested and purified. When administered to a snakebite victim, these antibodies bind to venom components, neutralizing their effects and facilitating their removal from the body. The success of this intervention, however, is highly time-dependent. The longer the delay between envenomation and treatment, the more extensive the damage that can occur, whether through tissue destruction, disruption of clotting, or impairment of neural function. In regions where medical infrastructure is limited, this delay can transform a survivable bite into a fatal one. This reality highlights a critical imbalance. The distribution of venomous snakes often overlaps with areas where access to healthcare is constrained. Rural communities, where agriculture and daily labor increase the likelihood of encounters, may be located far from facilities equipped to provide timely treatment. Transportation, availability of antivenom, and the presence of trained personnel all influence the outcome. In this way, the danger of a snake bite is not determined solely by the species involved, but by the context in which the bite occurs. The same envenomation that is survivable in one setting can be lethal in another, underscoring the importance of systems beyond the biological. The narrative reversal within this chapter emerges from the realization that the most dangerous snakes are not necessarily those with the most extreme biological capabilities. Instead, they are those whose lives intersect most frequently with human activity, whose habitats overlap with the spaces we occupy, and whose defensive mechanisms are triggered by our presence. The inland taipan, despite its formidable venom, remains a relatively minor contributor to global snakebite statistics because it exists in environments where encounters are rare. The saw-scaled viper, by contrast, becomes a significant threat not because it is the most potent, but because it is the most present. This reframing shifts the focus from individual species to the systems that govern interaction. Human expansion into natural habitats, changes in land use, and patterns of movement all influence the frequency and nature of encounters with venomous snakes. As landscapes are altered, the boundaries between human and reptile domains become more permeable, increasing the likelihood of contact. At the same time, cultural practices, education, and access to medical care shape the outcomes of these interactions. The danger is not static. It evolves with both ecological and societal changes. Returning to the initial moment, the footfall, the rasp, the strike, it becomes clear that the critical factor is not the speed of the snake or the potency of its venom alone, but the convergence of circumstances that bring predator and human into contact. The 10-second rule is a reminder of how quickly these circumstances can escalate, how little time exists between normal activity and life-threatening consequence. It is not a measure of inevitability, but of urgency, emphasizing the need for awareness, preparedness, and response. In the broader arc of this exploration, the patterns established in earlier chapters converge into a single understanding. Speed, as seen in the instantaneous strike, removes the possibility of reaction. Evolution, as demonstrated on isolated islands, refines organisms to operate within narrow constraints. Intelligence, embodied by species capable of selecting and pursuing targets, introduces flexibility and adaptation. Here, in the realm of human encounters, these elements intersect with reality, where biological systems meet human systems, and the outcome depends on both. The real strongholds are not defined by geography alone. They are constructed from interactions between predator and prey, between species and environment, between biology and society. They are systems sustained by pressure, shaped by constraints, and maintained through continuous adaptation. Within these systems, survival is not guaranteed by strength or speed in isolation, but by the alignment of multiple factors that together determine the balance between risk and resilience.